Hi everyone, welcome to another video for research design and analysis. In this series of videos, we're going to be talking about principles of sampling and how we can start using sampling distributions to start making inferential decisions about the data that we actually see in our sample. So this first video in the series is just meant to introduce us to the sampling distribution of the mean so that we can understand how the sampling distribution of the mean behaves when we change things like the number of observations that we're taking in our sample and what the variance in the parent distribution actually is. So relating samples back to the population, I think it's really useful in these instances to start with a known population, right? So again, this is not a situation we're actually going to encounter, but if we start with a defined population and then we simulate random samples, I think that provides us with a more conceptual understanding than walking through, some of the like closed form solutions for why some of these things arise. So let's start with a hypothetical population that has a mean of 0 and a standard deviation of 1. And here's our, I think I made this, 10,000 individuals who make up this population. So again, this is the population representing everyone we're hypothetically interested in. And this is also sometimes referred to as the parent distribution because the samples that we're going to take from this parent distribution are going to be kind of child distributions. They'll each have distributions of their own, but this is the overall parent distribution. So hypothetically, we could pull a sample of 10 individuals from here. So here, we've got, again, a histogram where we've got, one score basically for each person, except for a score of -1 or so, where it looks like we've got 2 people who had that score. This has a mean of about 0.13, a standard deviation of about 1.14. Right, so that's not too far away from what our actual parent distribution had, but obviously it's not exactly the same. And these things are going to bounce around if I take a different sample, right? So you can see here, now, okay, I've got a slightly more negative sample mean, a different distribution within the sample, and a slightly different standard deviation. And if I did this again, right, you can see now, okay, I've got a positive sample mean this time, a slightly different standard deviation. And again, these values are going to bounce around from sample to sample because the 10 individuals I have in each of my samples are always going to be different. So when we're talking about the sampling or the distribution of sample means, what we're going to be doing then is taking the mean from each of these samples that we've just drawn and thinking about how that distribution of sample means looks. So similarly, right, before we show these distributions, let's think about what happens if we increase the sample size. So, okay, now let's say I'm taking samples of 100 people from the same parent population. My first sample gives me a mean of -0.11, a standard deviation of 0.9. My second sample gives me a mean of -0.15, a sample standard deviation of 0.97. Right, and my third sample gives me a mean of 0.07, standard deviation of 0.98. Right, and again, we could keep doing this kind of over and over and take, thousands of samples if we wanted to. I'm just showing you the first 3 to kind of give you a sense of what we're doing when we're talking about these simulations and what it means kind of cumulatively when we think about the distribution of sample means. Now, the other thing to keep in mind in terms of what's going to have an influence on the distribution of sample means is the variance of this original population. So if I change the variance now to be a standard deviation of 2 in the parent population, you can see, okay, again, in a sample of 100 people, I've got a mean of about 0.19, standard deviation of 1.87, right? Then a mean of 0.09, standard deviation of 2.04, right? Then a mean of 0.06 and a standard deviation of 2.18. So by changing this variability, now I have more variability in the means of my individual samples, and naturally the standard deviation within each of my samples has gotten bigger. So hopefully this helps build up some intuitions about what it should look like when now we're talking about the distribution of all sample means, which we'll simulate by taking, rather than 3, we might take 10,000 samples. But you can also, through the central limit theorem, which we'll talk about in a moment, get more sort of closed form solutions for why these things actually look the way that they do mathematically. So as you can see, right, statistics in the sample tend to be very similar to the parameters in the population that we're trying to estimate, but they vary from sample to sample. Right? In any given sample, we're going to be taking different individuals, which means we're going to get a slightly different sample mean, we're going to get a slightly different standard deviation. But the really cool thing is that in the aggregate, the total number of samples that we take is actually going to have its own distribution. It's going to obey very specific properties that relate back to the parameters in the population. So we can better understand the way in which these statistics vary by looking at the distribution of sample means. You could also do this with the distribution of sample medians or the distribution of sample variances, but we're going to look at the distribution of sample means for now because that's going to be really important for kind of hypothesis tests that we want to run or the estimation of confidence intervals that we might want to do later. So let's think about the distribution of sample means now. So again, if this is our parent population, it's got a mean of 0, a standard deviation of 1. Here's the 3 samples that I showed you earlier. But now let's assume that I repeat this procedure 10,000 times. So now, instead of looking at distributions of individual scores, I'm looking at distributions of sample means over here. And this is across 10,000 randomly drawn samples. And you can see I get this nice normal distribution, which has a mean of basically exactly 0, right? And a standard deviation, though, that looks quite a bit different. So this is a standard deviation for the sample means of 0.313. which is a lot smaller than our standard deviation of scores, which was 1 over here in the parent population. So the distribution of sample means appears to be centered on the population mean, but its standard deviation is a lot smaller. than the standard deviation of the scores. Similarly, we can look at this now with n of 100, right? Again, we're drawing from the same parent population. Here's the 3 samples I showed you earlier, but let's assume I'm repeating this procedure over and over until we get 10,000 samples. We end up with a distribution of sample means that looks like this. Now you can see again, the mean of this distribution of sample means is pretty small. It's very close to 0, which is the true mean of the population. And its standard deviation, though, is even smaller. Now the standard deviation of the means is 0.098. So the standard deviation of this distribution when n is 100 is even tighter than this distribution when n was 10. So by increasing the sample size, I have reduced the standard deviation of the sampling distribution of means. They're both still lined up on the true population mean, but in terms of how much they spread out, that seems to depend on how big the samples are that I'm taking. The other key thing to notice here is that these distributions are symmetrical. So this means that any single sample mean that we take is going to be an unbiased estimate of the population mean, right? They're not always accurate. We have a lot of situations in which we don't get the population mean exactly right, but they overestimate as often as they underestimate. So that's a very desirable property of a sample statistic, because it's unbiased, right? Each individual mean might not be accurate, but in either of these distributions, we have as much a chance of overestimating as underestimating, so the sample mean is an unbiased estimate of the population mean. This also then makes the mean of the sample means, right, or what we're writing as mu sub x bar, approximately equal to the population mean. And indeed, if we increase the number of sample sizes here, eventually this would converge on precisely 0, and they would be exactly equal. However, right, like we said, these sample means do vary, and the amount that they vary appears to depend on the size of the sample. So you can see the variance when n equals 10, right, our distribution is roughly between -1 and +1, versus the distribution when n equals 100, when the distribution is between -0.5 and +0.5. So we can actually write this out more specifically, and there's a unique term for this standard deviation, right? So I said this was the standard deviation of the sample means, or sigma sub x bar, but in statistics there's a specific term for this type of standard deviation, and we call it the standard error, just to give it a little bit of conceptual distance, right? So standard deviation is the term we'll generally use for scores when we're talking about individual observations. The standard error is really just a special case of the standard deviation, but we reserve it for when we're talking about distributions of sample means. And the standard error of the mean actually has a mathematical relationship to the population standard deviation, where the standard error, right, or sigma sub x bar, is equal to the population standard deviation divided by the square root of n. So the standard error tells us how much we expect a sample of a given size to vary around the population mean, right? Because this is a measurement of variance, and we know this distribution is going to be centered on approximately the population mean. So, again, we use simulations, so we won't quite have perfect answers here. But if you actually use the closed form solution for this and you do 1 divided by the square root of 10, that would be 0.316. In our simulated example, we got 0.313, so that's basically within the tolerance to prove our point, right? Similarly, 1 divided by the square root of 100 should be 0.100. We got 0.098. Again, within the tolerance, those things are approximately equal. If we increased the number of iterations in our simulations, eventually they would become exactly equal. But the key thing to show you here is that the variance for the distribution of sample means is intrinsically related to the population variance and to the size of the sample that we're taking. So in summary then, most sample means are going to fall within the population mean divided by the square root of n, right? Or within one standard error of the population mean. In practice, however, we don't know the population standard deviation, nor do we know the population mean. Thus, we need to have some estimate of the standard deviation, right? And we need to have some estimate of the mean. And we'll use the statistics that we calculate in the sample as estimates of those parameters in the population. So ideally, we would like to know sigma, but we're going to have to estimate it using the sample standard deviation. And in the previous videos, we've talked about how if you calculate S, right, you can get an unbiased estimate of the population standard deviation. So it's not necessarily going to be perfectly accurate, but much like using the sample mean to represent the population mean, it is going to be unbiased. So if we do S divided by the square root of n, we'll have an unbiased estimate of the true standard error that we can use in different calculations. So again, right, we can see this then kind of working both ways. If we actually know a lot about the population that we're trying to study, we might have knowledge of mu and we might have knowledge of sigma. If those two things were known, then we could work from the population out to the sample and say, okay, if this is our population mean, most sample means will fall within -1 standard error and within +1 standard error of this mean. However, right, like we've often talked about, that's usually not the case, and we don't actually know mu and sigma. We're working from the sample back to the population. And in that case, if we know the sample mean, x bar, and we know the sample standard deviation, s, right, we can make an estimate of where the true mean is. Because if this is our sample, we can draw the same error bars around that and say, okay, well, we could go 1 standard deviation in the negative direction, 1 standard deviation in the positive direction, and those would be plausible population means that would have created this sample. Now, we can't say which one would have created this sample, right? Because this positive mu is just as much within the sampling error as this mu, right? But those would be plausible values of mu that could have led to this sample mean. In contrast, a population mean out here, we can effectively rule out because it is very unlikely to have given a rise to this sample mean that we're observing, right? That would be with, maybe outside of 2 standard errors away from the sample mean. So it's pretty unlikely that that's the actual mu in the population. So we can, we can't say that it is definitely not the case with 100% certainty, but we can say that this mean is unlikely to have arisen if this was the true value in the population. In contrast, this mean could have arisen if this was the true value or if this was the true value. And depending on the confidence we need to make that judgment, we might extend or shrink those error bars to make inferences from what we observe in the sample back to what seem like plausible parameter values in the population. So in subsequent modules, we'll explain these confidence intervals in more detail, and we'll talk about how we can use them both in the case of hypothesis testing and in estimation. And those things are intrinsically related, but often we might be interested in them for slightly different reasons or in slightly different contexts.